In this video, we will be reducing the communication in our parallel graph matching algorithm. We can reduce the number of proposals by sending motivated rejections. The motivation, if V proposes to U, but U has a better suitor, it would be then to send the weight of that suitor, so that you know that any proposal that has a lower weight does not have a chance. And if the U is already matched, then that weight would be plus infinity. And then no vertex on processor 5V will ever send a proposal again to U with a lower weight than that of the suitor of U. It may save a lot of proposals, especially at a later stage of the algorithm when weights have increased, weights of suitors. So then there are less likely proposals that succeed. Wedding rings. They are a sign of love, and they tell the world about a marriage, about a match that has been made. All the world, or, well, anyone at least who can see the wedding ring. In algorithms, the equivalent is to broadcast a match to all the processors in the vicinity, all neighboring processors. Proposing a match to an already matched vertex is useless. So we can broadcast the infinite weight of the suitor of V, meaning V has been matched, to a set of processors, and the set is P, the processor phi U, for all the UV that are in the edge set of S. Now this causes additional communication, and we would like to know how much that additional communication is. And we do that by finding an upper bound, and we make a number of assumptions. First of all, we assume that all vertices are matched during the algorithm, so the broadcast concerns all vertices. We also assume that all matches are broadcast. And then in the worst case, this broadcast is for all the original edges. Even though edges will disappear during the algorithm, we assume the worst case that we have the edge set from the beginning. And then the additional communication will depend on the partitioning at the start of the algorithm. To analyze this, we lay the connection between a graph and a matrix. And this matrix is called the adjacency matrix. For a given graph, it is defined by its zero non-zero elements. So Aij equals 1 if Ij is in the edge set, and it is 0 otherwise. So this way you get a binary matrix with only values 0 or 1. It's a symmetric matrix because the graph is undirected. So if Aij equals 1, also Aji equals 1. Same holds for the zeros. And the graph is sparse in general, so the matrix is sparse. And the diagonal of this matrix is 0, because we assume that the graph is simple, meaning it has no self-loops, and actually also no multiple edges between two vertices. Here you see a social networks. It's of dolphins. 62 dolphins that have been observed by biologists in New Zealand in the Doubtful Sound Fjord. For over 7 years they have been observed, and you see who is friends with whom. Altogether we have 159 friendships. So my question to you is, how many non-zeros are there in the matrix? I'll show you the matrix, and if you count, you see that there are 318. And the reason is, of course, that every edge causes 2 non-zeros in the matrix. So that we have 2 times 159 is 318 non-zeros. What we can do with this matrix, we can partition it in different ways and translate that back to our dolphins network. So we partition it, but we don't partition the matrix A itself. We add a diagonal to it, the identity matrix. And this really represents the fact that not only are you connected to your friends, you are also connected to yourself. So we add this. And then we have a matrix A plus I. And we can define a row distribution. Because if we have already a vertex distribution of the graph, phi, unknown yet, we have a corresponding matrix distribution, phi of A plus I. And then for index I, j, it is just phi I. So the vertex distribution determines the matrix distribution, and of course also vice versa. And since we are looking at matrix vector multiplication when we talk about partitioning sparse matrices, we also define vector distributions, and they are just the input vector and the output vector. They are distributed like V. And then we consider the matrix vector multiplication of A plus I times V gives U. When we feed this into Mondrian, into the partitioner for p equals 4 with an imbalance of 20%, then we get this partitioning of the matrix. And note that complete rows are assigned to processors. Row 0 is completely black. Row 61, the last row, is completely yellow. It has 4 non-zeros, which actually means that the dolphin numbered 61, his name is, his or her, I don't know, Zipfel, has 3 friends, 3 non-zeros plus a non-zero on the diagonal representing itself. Why do we add a unit diagonal? Well, this ensures that processor phi j, which owns vertex j, and hence also row j of the matrix, is also represented in column j. And then the remote processors that own non-zeros in that column, they correspond exactly to the remote processors that have a cut edge with vertex j. And that means that, and those we have to broadcast to. So the communication volume of the fan-out is exactly the same as the communication volume of the broadcasts. So the fan-out of the sparse matrix vector multiplication has a volume in the and it is exactly the volume of all the broadcasts of matches together in the matching algorithm. And note that since we have a row distribution, there is no fan-in, so the volume of the fan-out is actually the volume of the complete sparse matrix vector multiplication. So this is what we get when we translate the colors of the rows back to the dolphins. And you see that 4 different parts of the dolphin network and locality has been preserved, and that's because we use this local preference as a secondary weight. All primary weights are very boring because they are all 1. So this is in fact not a weighted matching, but it's a cardinality matching. And as a result, we get 23 internal matches and 1 external match. You see, by the way, the matches in green. Okay, we have a theorem about the connection between communication volume and edge cut. So V phi is the sum over all vertices V of the number of processors connected to it. So phi u such that uv is in the edge set, and phi u is not equal to phi v. This is the communication volume for a broadcast. Then we have the edge cut. That's the number of edges that is cut. The number of uv in the edge set such that phi u is not equal to phi v. Okay, so how do we prove this? We can start writing 2 times the edge cut of phi. The 2 will become clear why we write that. The v in v, the sum of uv in E of 1. So for every edge in E, we add a 1. Every edge connected to V, and we do that for all V. And then, of course, we're only interested in cut edges. And that way, every cut edge is counted twice. That's why I write this 2 here. Now this can be written if I'm looking at, again, all vertices. But now I'm splitting this into the processors S, between 0 and the number of processors minus 1. Only interested in the S that's not equal to phi v. And then I get the uv in E where phi u equals S. That's 1. So here we have expression where we split into the parts for the different processors, excluding the owner of V, because that cannot give cut edges. Now, I want to write this getting closer to the volume. So this is the sum of 1s for all edges connected to V that are in S. But I could also write this as a 1 if there is such an edge, and a 0 otherwise. And for this, I use an indicator function. The 1 of x is 1 if x is true, and 0 otherwise. So that I'm going to write here. So the first part I can just copy. S equals 0 to p minus 1. S is not equal to phi v. And then I write the indicator function of there is a u such that uv is in the set and phi u equals S. So it's clearly here I can get, if there is such a 1, I get 1 or more in this case. If there's no 1 in both cases, I get a 0. That's why this is larger than or equal to this. But look at what we have here. It says for all the processors, not equal to phi v, we get a 1 if there is a connection, if there is a uv in E with phi u equals s. So this is, and then I'm working towards the communication volume. This is the V in V of the total number of processors phi u for which uv is in E, and phi u is S. It doesn't matter which S. So phi u is one of those that's not phi v. And this is p phi. So we have shown in this proof that 2 times the edge cut is larger than or equal to the communication volume. That concludes the proof. So we have added costs for these match broadcasts. We also, and that's communication cost. So we also want to gain something. So in the worst case, we double the communication cost, because as we saw, we have an extra communication volume of at most 2 times the edge cut. And if you remember, in our algorithm, we had a cost already of 2 times the edge cut proposals, edge cut answers. And so altogether, in the worst case, we double the costs. But this is highly unlikely, because usually the volume is a lot less than the edge cut. If they are equal, it means that if we have a vertex connected to a number of other vertices with all these edges must be to a different processor. And often they will be to the same processor. So that is highly unlikely. Now what happens in the best case? Volume is usually a lot less than edge cut. And because we made these broadcasts, we never reached this upper bound of edge cut proposals. Many proposals are prevented. And so altogether, the communication cost will be closer to phi v. And that also means that if we partition for a sparse matrix, then this is exactly what we also need for our improved graph algorithm. We can further improve our algorithm, having this hypergraph-based partitioning, which we use for sparse matrix vector multiplication, but now also for graph matching. We can look at partitionings of matrices, not necessarily 1D, like with the row distribution, but just 2D. We can use, for example, the medium grain partitioning. If we partition then the matrix non-zeros. In graph terms, it means we partition the edges, actually also the vertices. This is more general. It reduces the communication by a lot. So this is also good for graph matching. And an additional advantage is, compared to 1D, if you have vertices with a very high degree, in the 1D case, they may completely unbalance the computation. And this effect is limited in the 2D case, because all the edges will also be spread across the processors. A disadvantage of a 2D matching algorithm, and that's why we showed only the 1D algorithm, is that they are more complicated. Vertices and edges will be distributed. And if you want to set a preference, you have to look at all the edges and their weights, but they are not on your own processor anymore. They are distributed as well across a few processors. So it becomes more complicated. Still, it will be worthwhile. Let's summarize. So we can reduce the total number of proposals by sending motivated rejections and by broadcasting matches. We have seen what the adjacency matrix of a graph is. It's defined by Aij equals 1 if and only if ij is in the edge set. And then we can add some communication by these broadcasts, but that is usually limited. An upper bound is phi v, and this is less than or equal to 2 times the edge cut, but usually it's a lot less. And we have seen that 2D matrix partitioning can further improve the algorithm. Now my question to you. Assume that the graph is dense. We have n vertices and all vertex pairs are connected directly by an edge. We also assume that we have a block distribution phi, where for simplicity we assume that P is a divisor of n. Now determine the volume V phi and the edge cut EC of phi. And what does this mean for a dense graph or a relatively dense graph?